streaming now. There we go. Hello and welcome back to Calculus 1 section 4.7 on L'Hopital's rule. It's actually Bernoulli's rule, but L'Hopital's rule. Anyway, so what is this rule about? Well, I'm going to go back to the good old limit x goes to 0 of sine x over x, and remind you that you were supposed to memorize that that limit is equal to 1. And someone might have said why, and I said wait, and eventually it will be revealed, and that's today. So here is why. So this L'Hopital's rule is going to take what we call indeterminate forms and through the use of derivative make the problem possible to solve, to take the limit. If you plug in x equals 0, because that's the most basic way to do limits, if you plug in x equals 0 into sine x and x, you will get 0 divided by 0. Now we know from chapter 2 that when you have 0 divided by 0, you better be able to do some algebra or some, witchcraft of that sort to transform the problem so that you can do it. And if there is nothing available to you, well, sorry, you can't do it. Until now. So there is no algebraic manipulation that you can do on sine x and x at the same time because they don't belong to the same field of functions. So you can't work algebra between them. So now what is this L'Hopital's rule? Well, it says if we have 0 divided by 0 or infinity divided by infinity, then limit x goes to 0 or infinity, so x goes to, I'll just put a, of f of x over g of x, and then you put this L apostrophe H, is going to have the same result as limit goes x to a of f prime of x divided by g prime of x. So this is the quotient rule. L'Hopital's rule. And I'm already thinking of the next thing that I want to write, and that is that this is not a quotient rule. Alright, so not a quotient rule. These are independent derivatives in the numerator and denominator. Maybe you want to write that sentence as well. These are independent derivatives in numerator and denominator. They have nothing to do with each other. It's like solving two derivative problems separately. It's exactly like that. Now, are these functions the same if you look at the limit on the left? No, they're not the same. That's why we have to put L apostrophe H, because the only thing that is the same is the result of the combination. So when you find the derivative of f, it's going to be f prime. When you find the derivative of g, it's going to be g prime. So is this going to be the same as that? Hell no. However, the answer of this and the answer of that in terms of the limit are the same. So that's the part that is important regarding L'Hopital's rule. So now, and by the way, we're done, right? That's it. That's L'Hopital's rule. We finished. But cases are now coming up. We are going to have 0 times infinity, infinity minus infinity, 0 raised to 0, 1 raised to infinity, 0 raised to infinity, right? We're going to have all of these different cases that can be converted into this. and solved. So L'Hopital's rule, as you can see, is a 10-minute thing, explained. Here is the example for it, and we are done with it, right? But then we have to take care of all of the other cases, which makes this lecture much longer than usual. So what is the limit as x goes to 0 of sine x over x? Well, when I plug in 0, I get 0 over 0, which means that this problem is of the indeterminate form. So if it is 0 over 0, and it is, I can use L'Hopital's rule to change this into the problem with the derivatives, which is derivative of sine is cosine x, and the derivative of x in the bottom is 1. Again, not a quotient rule. These are independent derivatives. That's all it is to it. So now, if you plug in your 0, cosine of 0 is 1 divided by 1, and the whole thing is 1, as you were asked to memorize back in chapter 3. So now when you ask why, here is why. And the answer is L'Hopital's rule. Another example would be one of those, remember the horizontal asymptotes and the infinite limits at infinity? That's another good example. So limit x goes to infinity of, let's say, x minus 3 over x squared plus 6. Now you know how to do this, right? You say, oh, the power in the denominator is larger, so it's 0. Okay, fine. Or you can divide everywhere by x squared, run the whole calculation, it will be 0. Fine. Or you can also use L'Hopital's rule. Because when you plug in infinity, on top you get infinity minus 3, which is infinity. And on the bottom you get infinity squared plus 6, which is still infinity. So you have infinity over infinity, which means that you can use L'Hopital's rule to take derivatives. So now you have 1 over 2x. So we transformed the problem that was, looking mean and evil into something that it's, when you plug infinity in denominator, we know it's 0, because when you chop 1 in infinite many pieces, you get pieces of size 0. So this is what we have for our calculation. And now, as I said, we are done with the L'Hopital's rule. You have an example for 0 divided by 0. You have example for infinity divided by infinity. So anytime when you have any of those two cases, you will immediately take L'Hopital's rule, meaning you take those derivatives, and then you plug in the value again. Sometimes you might have to do L'Hopital's rule 2 or 3 times. That's okay. You can chain them, right? As long as you're getting 0 over 0 or infinity over infinity, you can do L'Hopital again and again and again. As soon as any of those 0 or infinities are lost, you get 1 or 6, you're done. You can't do it anymore. It only works when it's 0 over 0. And you can chain as many as you want, as you can, as long as it persists to be one of these cases. So that's L'Hopital's rule. Done. Now we are going to take a look at cases that arise for limits where you can transform them to what you see over here. So here is 0 times infinity case. So 0 times infinity case is case when you plug in your values and you get 0 times infinity. Now we use f of x is equal to 1 over f of x. So we use this algebraic trick. here I'll write that algebra trick, if you want to use that word. So we know this is okay, this is fine, because if I multiply function in the numerator and denominator, it will cancel in denominator, and you just have f over 1, which is f, right? So we know this is all good. Now let's take a look at a problem. Evaluate the limit as x goes to infinity for x squared times sine of 1 over 4x squared. Wonderful limit, right? Oh, by the way, what is 0 times infinity? Anything times 0 is? 0. And anything times infinity is? So which one is it? You see that? Yes.
So we just have to have like a limit in the first place for this to actually work?
Yeah.
Okay.
But see, now we're talking about multiplying 0 times infinity, and we want to see what it is, because, right, we cannot make our minds. Can you give me a valid argument why this should be either 0 or infinity? And the answer is no, you can't. Right? Because you learned so far anything times 0 is 0, anything times infinity is infinity. So what happens if I pick those anythings to be 0 and infinity? Like, which one wins, right? So these are the very interesting things to, I mean, they're interesting to me. I don't know, where you stand with this stuff. But for me, this was fascinating, because I always had that belief, oh, anything times 0 is 0. So can't I just put 0 here? But then you see that infinity and you say, And then I wanted to learn it. So what do I have? When I plug in infinity for x squared, I get infinity. When I plug in infinity for x squared in the sign, I get 1 over infinity, which is 0, and sine of 0 is 0. So I do have infinity times 0 case. So I'm going to use f equals 1 over f, which means that this x squared is going to go into the denominator as 1 over x squared. So this is the same. Now, guys, this is not L'Hopital's rule. This is algebraic manipulation, right? So this is sine over for x squared divided by 1 over x squared. Observe that I did not put L'H, because, as I said, this is algebraic manipulation, has nothing to do with L'Hopital yet. Now you test again. Plug in infinity. What do you have on top? 1 over infinity is 0, sine of 0 is 0. And what do you have at the bottom? 1 over infinity, which is also 0. Yay! Using this algebraic trick, I was able to transform the problem into 0 over 0. This is the part where you go and you use L'Hopital's rule. So now, this is equal to L'H, limit x goes to infinity, and now I have two independent derivatives. Well, the bottom one should be negative 2 over x cubed, right? And now the top derivative of sine is cosine. That's 1 over 4x squared. And then I have to take the derivative of this, which would be negative 8 over x cubed. Because I know that, 1/4 times 1 over x squared. So if I already know what the derivative for 1 over x squared is, which is negative 2 over x cubed, then I just need to multiply that by, this is supposed to be negative 1 over 2. There we go. Right? Is that better? Because it's 1/4 times negative 2 over x cubed. And then these cancel, so negative, okay, good. Great. what I'm going to do is I'm going to multiply x cubed top and bottom. How about we make that x cubed over negative 2a, yeah? That will actually clear more stuff at the same time. So that's limit x goes to infinity. And then now I have what? Denominator completely cancelled, so that's dead. I still have the cosine of 1 over 4x squared. And what is left with this? X cubed is gone. It's 1/4 in front. That's all it is. So now, what's cosine of 0?
1.
So 1/4 times 1 equals to 1/4. Woohoo! Isn't this great? 0 times infinity equals a quarter. Who knew, huh? Yes.
Won't you like simplify that by instead and multiplying by your central one squared? Like you shut it out and you multiply by the upside down side.
Well, it's cubed, not squared.
The second,
This
where
one,
you
right?
have 0 over 0, basically, before the left over.
Here?
Yeah, more algebraic manipulation, basically. You shut it out. Make it sine 1 over 4x squared times the reciprocal.
But then you got to go back here.
Oh.
We use the trick to transform it into this. Because if you flip this up,
I'm relying on pre-calculus bullshit, never mind.
All right. Well, there you have it. 0 times infinity equals a quarter. Awesome. Now, obviously, if I want to change that fraction, I'm just going to adjust this number into something else. See what happens through your calculation, right? You pretty much know what will happen, right? So, we can make 0 times infinity to be anything. Isn't that great? You wake up in the morning, how about today we have 0 times infinity to be equal to 27, right? And then you go and you make up the problem that will work out to be 1 over 27, right? And there you go. So it's really, really interesting stuff. So that's 0 times infinity case. 0 times infinity case, you will always transform one of the two functions, and then you transform one of the two functions, put it in the denominator using that algebraic trick, and then you just follow algebra from there. Obviously you have to do derivatives and then cancel and then follow the algebra to get the rest. That's that part. How much is infinity minus infinity? Zero is a possible answer, right? Also, we could say infinity, but it also could be 2/3. I don't know. let's take a look. Wouldn't it be nice if it's a quarter again?
What kind of implications does this have for like practical engineering stuff?
How about you renormalize your renormalization for the string theory?
Yeah, I don't know anything about that.
So right now it's just extremely cool, right? And then later on you need some mathematical witchcraft to deal with some serious issues of modern physics that we have. It gets rooted here and then expanded obviously through levels of and layers of math, but yeah, there is stuff. And also the interesting part was what is it, 2 weeks ago or so, one of my past students sent me the message asking me to help with the limit. He's a computer science senior at Rutgers, taking the 400 level courses. So he messaged me with this one limit, and I said, L'Hopital's rule, man. And he goes, oh, I forgot about L'Hôpital, spelled it with S, by the way, and hospital. So, I forgot about L'Hôpital, right? And then maybe 30 minutes later, capital letters and the message say, and L'Hôpital comes in a clutch and solves all 5 problems on my homework set. So apparently all 5 problems that were assigned for that week in this 400 level computer science course were actually limits that had to be solved for whatever they were doing. I only seen 1 of those 5 limits, and he said that obviously he immediately went to Calculus textbook, reviewed the whole thing, and seen that the section solves all 5 problems. So guys, you're gonna see this later on. All of Calculus you're going to see if you're in an engineering track. So just stay tuned and mentally invested at all times. How about we take a look at the limit? It's an interesting one. X goes to infinity of x minus square root of x squared minus 3x. This is amazing. Now, what's application for this particular problem? Absolutely nothing. This is what we would call mathematical gymnastics, right? You go and you just show that you can jump over that pole, but you don't actually go and jump over fences and things like that when you're as you're going grocery shopping or something. You jump over the aisle. You definitely can, but you don't do it. So this is the same. This is the same idea, right? You can do it, just you don't do it anywhere. L'Hôpital's rule is 0 over 0 or infinity over infinity. I have a subtraction here. How do I go from subtraction to division? Like, what are the steps that we have to take in life to transform a problem that is subtraction into a problem that is division?
Has to be subtracted with multiple times, with addition with multiplication.
So multiplication. Yeah. So to get to division from subtraction, you have to go through multiplication. Now, how do you obtain multiplication out of subtraction? What mathematical manipulation, witchcraft, whatever you want to call it, transforms nope.
X over whatever it was solved for him.
It's a single F word.
Fractions.
No.
Single F word.
F word, yeah. That transforms the subtraction into multiplication. Factoring, exactly. That's the one. So, we factor, right? Now, in order to factor where that minus sign is, I better have x and then another x so that I can factor it out. And when I factor that, I'll be able to have multiplication. Then we have the trick, right, to change multiplication into division. Remember this trick? This trick was changing multiplication into division. So, yeah, these problems tend to be, didn't I say, right? And I only had 2 of you warm up your wrists. This is going to be a page or so. So, let's go. What do I need? I clearly need an x over here so that I can factor it out with the other x. So, if I need an x there, then it has to come from within the root. So we need x squared under the root so it can escape as x. Okay. So the first thing is to factor x squared inside. And that's going to be 1 minus 3 over x. Note that the second term does not have x squared. So you have to multiply it by x over x to make it x squared. And that's how you end up with a 1x in denominator. So we multiply over here x over x to make x squared, and then you are able to factor out x squared. So now, limit x goes to infinity. I can kick this x outside, and finally I have this situation. Kick x outside, and I have 1 minus the square root 1 minus 3 over x. Whole ton of algebra. We already factored twice. And finally I have multiplication. Plug in infinity. Let's see what happens. Try yourself to plug in infinity. Wait, is it supposed to snow today?
What was in Alaska?
No, you remember the visitor before the test? He's driving, it's just snowing, going up. So is it coming?
North Jersey?
Yeah. He posted. Here, I see him driving.
Oh, maybe in Sparta or something like that, right?
Well. All I would say is please no. All right, so what is the verdict? The verdict is infinity times 0, right? Because 3 over infinity is 0, 1 minus 0 is 1, square root of 1 is 1, 1 minus 1 is 0. There we go. Good. So now we use f equals 1 over f to finish this problem. And we have limit x goes to infinity. 1 minus the square root of 1 minus 3 over x divided by 1 over x. What do we have now? We have 0 over 0. So this means that we can use L'Hopital's rule to get limit x goes to infinity. I'll keep forgetting writing these equal signs. So L'Hopital's rule, limit x to infinity, we take two independent derivatives. The one on the bottom, easy, right? So just negative 1 over x squared. We have to deal with the derivative on top, and that is some chain rule and some fun, right? So what do we have? This is technically 1 minus 3 over x raised to the negative 1/2. That's what it is. So derivative 1 is 0. We have positive 1/2 because, no, actually this is, it's just 1/2. So it's negative 1/2. 1 minus 3 over x to the negative 1/2 times the derivative of the inside, which is negative 3 over x squared. There we go. No, it's positive, because there's a negative inside and the negative from the derivative, it's positively expected. So now I am going to multiply numerator and denominator by negative x squared to completely kill off the denominator. So now more algebra here. That's limit x goes to infinity. What do I have? I have positive 3/2. X squared is gone, x squared is gone. So positive 3/2. And then I have 1 over the square root of 1 minus 3 over x. Is that good? Yep. And now when you plug in infinity, you get 3/2 times 1 over 1, which is 3/2. And I have there we go. That's it. So what's infinity minus infinity in this case? It's 3/2. It's 1.5. You can't even plug this in a calculator, right? Let's see if we can find one more example of this, because there are certain examples that are not done exactly this way. So I just want to find at least one of those. Tangent minus secant. Great. So limit for 0 plus, no, pi over 2 minus. Limit x goes to pi over 2 from the left, right, minus. And then we have tangent minus secant. So tangent x minus secant x. So try this one a little bit. This is another infinity minus infinity case. Okay. Let's take a look at this together. So this is infinity minus infinity. So what can I do? Limit x goes to pi over 2 from the left. I write tangent as sine over cosine minus 1 over cosine. and then I factor out 1 over cosine, left with sine x minus 1. So now x goes to pi over 2. So when I put this together, I have sine x minus 1 over cosine x, and this is 0 over 0, because sine of pi over 2 is 1, minus 1 is 0, and cosine of pi over 2 is also 0. So I have 0 over 0. We can do our derivatives now. Go pi over 2 minus. That derivative of sine is cosine x, and derivative of cosine is negative sine x. 0 over 1, which is 0. So in this case, infinity minus infinity is 0. Woohoo! What's left is 1 to infinity, 0 to 0, and infinity to 0 cases. They're all solved the same way. So how much is limit? X goes to infinity of 1 plus 1 over x raised to the x. Well, plug in infinity. 1 over infinity is 0. So this is 1 to the infinity case. Make sense? So how much is 1 squared?
1.
And 1 cubed? And 1 to the 10th power? And how about 1 to 11th power? Also 1, right? So it makes sense that 1 to infinity should be 1, right? Okay, good, because it's not. This was also one of the cases where I said, really? Let me not sleep like 2 days over this, just to make sure that I have my sanity in check. So how are all of these guys solved? They're solved by writing y equals limit x goes to infinity of 1 plus 1 over x raised to the x, and then we ln both sides. Ln is the only way where you get to peel off the exponent, right? That's the part that bothers you, the exponent. So you need to get rid of that exponent. And the way to get rid of that exponent is to have ln so that you can bring it up. So you remember the formula that ln x to the p was p ln x, right? So that p jumps in front of the ln. So now we have that ln y is equal to the limit x goes to infinity x ln 1 plus 1 over x. So exponent jumps down. When you check infinity, you get infinity times 0, because ln of 1 is 0. And this is where you use f equals 1 over f. Anytime you have 0 times infinity. So ln y is equal to the limit x goes to infinity. We have ln of 1 plus 1 over x divided by 1 over x. When you check now, you will get 0 over 0, which will, 0 over 0, which is now L'Hopital's rule. So ln y, and we put L apostrophe h now because this is L'Hopital's rule now. So limit x goes to infinity, and now we have to take these derivatives. Negative 1 over x squared in denominator, that's the easy one. Numerator, what do we have? Well, we have ln. And the derivatives of ln's are easy because you take the argument, you write it as is in denominator, and you put its derivative on top. Well, what's this derivative? It's negative 1 over x squared. Well, great. Those cancel. And the only thing you're left with is that ln y is equal to the limit x goes to infinity, and you have 1 over 1 plus 1 over x, which is equal to 1. Because 1 over infinity is 0, plus 1 is 1, 1 divided by 1 is 1. So there we have it. So we have ln y is equal to 1. How do I solve for y? How do I solve for y? We e both sides. So y equals e to the 1, which is e. Now y was the whole problem, so limit x goes to infinity of 1 plus 1 over x to the x is equal to e. And that's the definition for e, exactly. Yep, right there. Definition for e. Since we don't have time in class, I will have to do one more thing the next time we meet, but I just want to make sure that you guys have this problem. So when you learn this at home, try this example, sine raised to tangent. So limit sine x raised to tangent x as the exponent as x goes to 0 plus from the right. Here I'll put the just do it. You will write y equals everything. You will ln both sides. Tangent will push. Tangent will come down, and then you just go through the steps. All right. Bye.